As far as I am concerned, you are a graduating senior high school student from the STEM strand. Oh, it seems that you're just new to college life and having no one to lean on with regards to engineering subjects. Or maybe you are already a college student who needs to keep going in engineering until graduation. Don't worry, cause I got your back, pal. Wait! Before anything else, let me introduce myself to you. Hi, I am John Kenneth Gonzales, together with my groupmates, Shaina Gatlula, Shania Morales, and Shaira Alagon. Too many S's, isn't it? Anyway, today we are going to discuss something really important when it comes to engineering, derivatives and integration. As officers of the student organization and the eldest in the College of Engineering, we are tasked to encourage fellow young students like you to pursue their chosen field of study through this presentation, highlighting the importance and applications of the derivatives and integration in the field of engineering. But first, let me define these two mathematical terms. First of all, what are derivatives? Derivatives or differential calculus are a fundamental tool of calculus. The derivative of a function of a single variable at a chosen input value when it exists is the slope of the tangent line to the graph of the function at that point. The tangent line is the best linear approximation of the function near that input value. We use derivatives to determine the maximum and minimum values of particular functions such as cost, strength, amount of material used in a building, profit, loss, and the like. Derivatives are met in many engineering and science problems, especially when modeling the behavior of moving objects. On the other hand, integration or integral calculus is a way of adding slices to find the whole. While differential calculus focuses on rates of change, such as slopes of tangent lines and velocities, integral calculus deals with total size or value, such as lengths, areas, and volumes. As a result, much of integral calculus deals with the derivation of formulas for finding antiderivatives. Integration can be used to find areas, volumes, central points, and many useful things, but it is easiest to start with finding the area under the curve of a function. Now, let us have a closer look at these two foundations of engineering using real-world situations. I will now let my groupmates handle this for you.
Suppose you are making a box out of a piece of cardboard measuring 9 square inches by cutting equal squares out of the corners and turning up the sides. Find the volume of the largest box that can be made in this way. To successfully solve this problem, we need to visualize the data first. Since it is stated that 4 squares of equal sizes should be cut, first to create a box, we can represent each side of these squares as x. Knowing that one side of the whole cardboard measures 9 inches, we are now able to know that the remaining unknown part of each side is 9 minus x inches or 9 minus 2x inches. Once the cut cardboard is folded, the material would make a three-dimensional box with top side open, having x as the height of the box. Now, to find the volume of the box, we would want to substitute the data. Using the formula volume equals length times width times height, we will have the following solution. Then, we will now be using derivatives to know the value of x or the height of the cardboard box. Simplify further using quadratic formula, and there you have it. We will obtain two values of x, one absurd 4.5 inches and one real 1.5 inches. If we are going to use 4.5 inches as the value of x, we will obtain 0 cubic inches as the minimum volume. On the other hand, if we will use 1.5 inches as the value of x, we will obtain 54 cubic inches as the maximum volume. Therefore, if we are to transform a 9 square inch piece of cardboard into an open box, its volume will become 54 cubic inches as the maximum possible volume. Doing the same procedure will give you the right answer in problems similar to the previous problem, whether the shape of the box is a cube or a cuboid.
The first problem discussed is actually related to architecture. Now, let's focus and dig deeper into engineering through this problem regarding derivatives. A Norman window consists of a rectangle surmounted by a semicircle. What shape gives the most amount of light for the given perimeter? First things first, since there are two closed figures mentioned in the problem, rectangle and semicircle, we will be using their respective perimeters to proceed to finding the right answer. Except that one side of the rectangle will be omitted from the exact window figure. So, combining the perimeters of the rectangle and semicircle, we will have the following equation, where b equals twice the radius of semicircle and r equals half the base of the entire window, or just the radius itself. Substituting the said values, we will have the following solution. Then we will now be using derivatives to know which of the two shapes of the Norman window gives the most amount of light. Having as the derivative of the height of the window, we will now substitute it to the combined area of the two shapes. See the following solution yourself. Finding the derivative of the area, substitute the derivative of the height we obtained earlier, simplify further, and there you have the final answer. H equals b, or height equals base or width. Therefore, both shapes composing the Norman window gives the most amount of light for the given perimeter. Another problem involving derivatives is this. This one is more into engineering, as you are about to see. Two posts, one 8 feet high and the other 12 feet high, stand 15 feet apart. They are to be supported by wires attached to a single stake at ground level. The wires running to the tops of the posts. Where should the stake be placed to use the least amount of wire? In this problem, we would want to find the length of the two wires first. We can do this using the Pythagorean theorem, where C is the hypotenuse or the wires and A and B are the posts, and the distribution of the total length of the ground from one post to another. Here is the solution. Then, we would want to add the lengths of the wires and get the derivative of the result, so that we will know where the stake should be placed within the given ground length. Going fast forward, we will have two values of x, where one is meaningless and the other is the right and legit answer. Therefore, the stake should be placed 6 feet away from the shorter post to use the least amount of wire. These problems are some of the many applications of derivatives or differential calculus in the field of engineering. Let us now discover more about the application of integration or integral calculus in the said field.
Integration is the easiest to start with finding the area under the curve of a function. So, we will use it to find the area of a certain nuclear power plant of the Philippine Department of Energy located in Quezon City, at two specific points as illustrated below. The unit of measurement to be used is meters. First, take note of the given values of x, 1, and 4. We will use this as substitution of the following equations. So what we have now is the algebraic expression with x is equals to 4, minus the same expression but x is equals to 1. Simplifying further, we will have the final answer of 10.5 square meters, which represents the area of TOE's power plant with the base measuring 3 meters distributed proportionally. This problem looks easy, but the next problem is a little bit trickier, so kindly allow me to explain it to you as you listen very well. The The figure shown below is composed of arc of circles with centers at each corner of the square 20 by 20 centimeters. Find the area inside the square but outside the region commonly bounded by quarter circles. The required area is shaded as shown in the figure below. A problem involving the same area was carried out by geometry without involving any integration. Then we will have the area of shaded region is equal to the integral of 20 minus the square root of 20 squared minus y squared from 0 to 10. At this point, you can use your scientific calculator to solve for the area of region ABC. But for the sake of discussion, integration is carried further step by step below. After getting the shaded region, multiply it by 8 for the sake of the other similar regions, and there you have it. The final answer for this problem is 69.42 square centimeters. In real-world application, a theme park having a same dimension and structure will have 69.42 square meters for the construction of gardens and other structures that will make the park more appealing and accommodating to visitors.
Having learned the basics and depths of derivatives and integration, we now know that differential and integral calculus are both indeed a very important part of engineering, as it helps us know the exact measurements of worldly things, such as their areas and location. Without these, every building and infrastructure in this planet wouldn't be successfully constructed as planned. Thanks to their pioneers, Sir Isaac Newton and Gottfried Wilhelm Leibniz, for introducing such fields to the huge world of mathematics. Thank you very much for watching this video. We hope that you have learned a lot while having fun exploring the complexities and real-world applications of some of the hardest subjects under engineering. We are also looking forward for you to become one of our co-engineers in the near future. Again, I am John Kenneth Gonzales, and together with my groupmates, we would like to leave a very inspirational quote that will surely keep you pursuing your dreams. Aim high and hit the mark. Also, don't forget to check out the editor's YouTube channel and subscribe. That's all. Bye!